Welcome back. This is video number 6 of your module 6 on traffic assignment. And in this video, we're going to talk about incremental method. By now, you should have been convinced about three things. Number one, all or nothing, all or nothing assignment is not realistic. Okay? All or nothing assignment is not realistic because people are going to take more than one route. You may take the same route, but if you take a group of people, they may not take the exactly same route. So the second one we talked about is stochastic assignment is incredibly complex. All right. And it becomes so difficult to model using that method. It may be realistic, but it is incredibly complex. So there's probably not the right, well, it may be the right one if you can find the right equations of utility and what have you. And the third thing you learned in capacity restraint is that as the flow increases, travel time kind of changes with flow, volume to capacity. How do we incorporate that into traffic assignment? So if you're not convinced that all or nothing and stochastic are not the right ones, at least at this point, so just take my word for it and then pretend that you're convinced. Okay, now let's try to do slightly better than all or nothing and stochastic with some other by a mechanism with which we can incorporate the relationship between travel time and volume to capacity ratio. That is essentially what we start with a method called incremental method. One other thing I want to mention, this method is not that used now, but in the beginning it was very popular, but it's important to learn the evolution of this traffic assignment techniques by studying some of the things that are not being used, even though they are not being used today. And that's why we are studying incremental method. So the philosophy is going to be simple. You have one bucket of trips going from A zone to, origin to destination, and take that bucket and then assign them in increments. Take some percentage now and some percentage in the next iteration, and the third iteration and fourth iteration, like that. Speaking of iterations, one of the reasons why we do iterate is that volume to capacity ratio is dependent on, the volume assigned is dependent on travel time, and travel time is dependent on volume to capacity ratio. So they kind of dependent on each other, which is the reason why you do an iterative way to recurse. So that's why we are doing the iterations. So each time you go from one iteration to another iteration, you will compute the new travel time as a function of volume that is assigned thus far. So it's just a generic way of representing. So how do you update the volume? I'm sorry, as a travel time. How do you update the travel time? Based on one thing we used is BPR function. All right, so that's one option we have available for us. So what are the steps? First of all, you find the path for each zone. It's a path tree. You remember we talked about path tree using shortest path algorithms. So we have done that. So find the path tree and then assign a portion of the trip exchange matrix in increments. First increments, this is the usual way they assign it. Take 40% of the trip matrix. Let's say you are assigning trips from A to B. Take 40% of the trips that go from A to B, assign them on the network, and then go to the next zone, process it, next zone, process it, etc. It goes like that. And each time you finish all the zones, processing all the zones, then update the travel times of each link in the network. Each link, there may be 100 links or 10,000 links. You have to update the travel time of all the links. And repeat this until all trips are assigned. In this particular case, it takes 4 iterations to do that, and sum them all up towards the end. That's essentially what it is. You can easily understand this with an example, which is where we are headed. So here is a simple 3-link problem, 2-zone, 3 links. The first link has, it's the same thing we used earlier to do the all or nothing or stochastic assignment, but slightly different travel times. So you have link 1 7-minute travel time, link 2 10-minute travel time, and link 3 16-minute travel time. And the trip exchanges between A to B, we are only doing A to B to illustrate this, are 100 trips. And recognize this is your BPR function, which indicates travel time as a function of volume capacity ratio and free flow travel time, right? That's what this function is given. So all these 3 links have this travel time relationship, and the capacity of each link, which is denominator here, being 30. So at the end of each iteration, you will have a different volume which dictates the new travel time. That's the idea here. So the steps we talked about earlier: assign 40% of the trips, which is 40% of 100 is 40. So 30% of trips is 30, like that. So assign them 40 in the first iteration, 30 in the second, etc., etc., etc. Now, if you are just looking at the presentation and this slide is incomplete, meaning if you just look at it without the work that is being placed on it, is useless by itself. So pay close attention to what I'm doing here. So what are the 40% of the trips? It's basically 40% of the trips are 40 trips from A to B, and they go on all or nothing path at this point. The shortest path, all or nothing of these trips will go on the shortest path. The shortest path being 7 minutes in the current condition, in the current network condition. So I'm going to put 40 on this road. Now they're going to be 0 and 0 here. So if I want to, this is easy to update. So the volume is 0 to L3, so I'll put 0 there. The volume is L2 for B, which is 0 there. So the travel time here is T0 is 10, and in this case T0 is 16. The travel time here is going to be still 10 and still 16. But things have changed here. T0 is 7 and the volume is 40. Yeah, when I compute, you get this value to be, okay. When I compute this, I get the value to be 10.32. 10.32 minutes. So you might as well strike this off and say for my next iteration, the travel time on link 1 is going to be 10.32. So let's move on to the next iteration with this state of the network. So the state of the network from previous iteration is like this. So you have link 2 volume of 0, link 3 volume of 0. I forgot to put it up there. And now take a look at the network. which one has the shortest path? Now, our next job is to assign 30% of the trips or 30 trips. 30 times 100, 30.3 times 100 is 30 trips. Now, which one is the shortest path? And here is the winner. L2 is the winner. Now, what we are going to do is put all these 30 trips here. So, I should probably erase this here because we are going to put 30 trips here, or maybe you can keep it. 1 second. I'll do that. 0 plus 30. 0 indicates in the first iteration it has 0. So now you have new set of loadings. In link 1 you have same 40 travel time, 40, and t sub 0 is 7. So you will not, this will not change, 10.32. And link 3 still has 0, and this guy here volume is going to be, I'm sorry, not t0, here it is not 0, so travel time here is 16. So this free flow travel time is 16, that's going to be there. So this will come out to be still 16. Come on, this is the problem with technology. So let's say this is still 16, and what you have here is travel time of free flow travel time of 10 and a new volume of 30, which makes exactly, it's a volume capacity ratio of 1. So in this situation, what you will get is 11.5 minutes is the travel time you're going to put. So you might as well cross this off and say at the end of this iteration you have 11.5 minute travel time. So this is the state of the network at the end of iteration 2. We enter iteration 3 with this state, with 40 traffic of 40 on link 1, traffic of 30 on link 2, and the travel times in this state. So let's see who's the biggest contender in terms of shortest path. This time link 1 is back in play again, which is 10.32 is lower than 11.5 or 16.4. So we are assigning 20 trips in iteration 3. 20% of 100 is 20. So this path gets the 20 more. Now, at the end of this iteration, you will have 60 trips on link 1, and your free flow travel time is 7. So that will bring your travel time is to 23.8. 23.8. Since we do not have any update here, so you can leave it, or just for completion's sake, let's put the values there as 10 free flow travel time and 30 volume gives you 11.5. Here 16, this guy still has 0, and this is still 16. So what we are going to do, we might as well strike this off and put 23.8 here. So you have 40 plus 20 is a total of 60 there, and you have 30 here. Now we go to the next iteration. So in the next iteration, the remaining 10% of the trips are going to be assigned, or 10 trips are going to be assigned. Now the state of the network that was left at the end of iteration 3 looks like this. 60 being assigned here and 30 being assigned, 10 more waiting to be assigned. Now who's the contender? Which link is the shortest between A and B? That is this link, which is link 2. So with the travel time of 11.5, so 30 plus 10, you have 40 here. And then there you go. Since we did not add anything here before, we have 60, and leave that as 60 you may. And here you will have 7 times that, you still have 23.8, and this guy still remains because there's no, that's an orphan link which has no loading. We are done assigning, therefore its travel time is still 16. And now something changed here, which is your free flow travel time of 10, and then you have 40 trips assigned, and that comes out to be 14.74. 14.74. So this is the state of the network at the end of fourth iteration. Let's summarize that. Summarize we did. There you go. Oh, wait a minute. Is this 46? Actually, this is incorrect here, not 46. What I posted earlier is correct, 14.74. It's something, 46 is for the next variation of this problem. So I kind of like cut and pasted in a bad way. Anyway, so this is the actual state of the network. So you incrementally assigned 100 trips, and it brought 60 trips onto link 1, 40 trips onto link 2, and 0 trips onto link 3. Free flow travel time, still maintaining free flow travel time on link 3, whereas link 1 went to 23.8. Just by looking at it, you can see how, shall I say, ridiculous it looks. Because who in the right mind will get into a road? It's like 2/3 on this link, not 2/3. 60% on this. Well, 60% on link 1 with the worst travel time possible. So, realistically speaking, well, it's not realistic. So this term loaded network comes from, we have now loaded everything onto this network, and the network picture, it looks like this, and in a report it looks like this. You will have volume and travel time by identified by link. So that is essentially the incremental assignment. So what I did here is I reduced the capacity by 25%. Remember, we were given capacity of 30, well, whatever the units are, the capacity of 30 is given. So if you reduce it by 25%, 0.75 times 30 is 22.5, 22.5. If you use capacity as 22.5, why would one reduce capacity by 25%? Well, take for example, you take one lane away for construction, or maybe there is, you haven't cleared the snow, or whatever reason. There may be a reason for you to reduce the capacity. So in situations like that, you can still do the same problem, but in the denominator, in the volume to capacity ratio, you have 25% less. And in that case, so this guy, link 1 gets 40, link 2 gets 50, link 3 gets 10. So he's not an orphan anymore. Now here is a spreadsheet I used. I used this spreadsheet to do all the computations. Let's see what this spreadsheet, actually you can, I will not be sharing this spreadsheet immediately, but towards the second set of assignments I will share that to you. You are welcome to create your own spreadsheet. That's one way to learn. But let me explain what I had done here. So for iteration 0, when we started, you have t. When you say iteration 0, that t sub 0, which is essentially the free flow travel time. For iteration 1, see this 40, that 40 is assigned on the shortest path. So how do I know which is shortest path? I visualized and then found out this guy, this is L1, has the shortest path. So I assigned 40 on that one. My spreadsheet gave me the travel time. And looking at these updated travel time, I looked at the next contender is this one, which is L2, assigned the next 30% on L2, updated the travel times. Now look at this thing, and still I have link number 2 as the contender, added the other 20% over there. So you get the picture. So this is this spreadsheet, what you are seeing is for the 25% reduction. So now don't be fooled by looking at the simplicity of this small network. I visualize the path and then able to do the assignment. But if I just added one more link here, it gets complicated. Two more links, and about maybe 10 or 15 links, your mind starts to wander. You have to have a pathfinding algorithm to do that assignment for you. So that is essentially what I wanted to talk about on incremental assignment, and the next video is going to be on iterative assignment. So this concludes your video number 6 of module 6. This video is on incremental assignment.